As you can see from the title, so I'm sort of one of you guys. I was at, Katie mentioned I was at Microsoft Research Asia, Beijing. It's the same group where the residual network was invented by my team member, Kai Ming and Sun Jian. So at the time, of course, we were all experiencing computer vision. I'm also working on computer vision, right? So there's been very practical tools, deep networks developed about 10 years ago. Has really changed, significantly improved a lot of the practice, especially high dimensional data. Come with a lot of mystery, right? Many actually go against the traditional classical understanding of why the capability, as well as many phenomena associated with it, was not able to explain by traditional theory, let's say in signal processing, data processing, statistics even, or optimization. So for many years, I was just like you. When I came back to Berkeley, I was able to focus a little bit on research. In the beginning, also try to understand what's going on, since it came from my former group. I gave myself the charge that I was trying to understand a little bit about it. So in the beginning, again, we were just like everybody else, trying to understand a little bit of every bits and the pits of the networks, right? What happens, with dropout, why mobilization, why ReNU, why some kind of property, how to make the network stability, why it's stable, why it's lack of robustness, and so on and so forth, right? There's many topics on there in the past few years. You may see hundreds, thousands of papers trying to understand bits and pieces of it. So the story came, around 2019, I was visiting New York, Young LeCun. He got the touring award, we were friends, so we were chatting in his office. So for a whole afternoon, we're asking, right? It actually baffles me, also baffles him, is that what neural network is trying to optimize, basically. That was the topic. That's end of November 2019. Now, after that, everybody know what happens, right? The pandemic hits. So they sort of gave us a little bit of time to think about, everybody, including my students. So after that, I sort of realized that the topic is getting a little bit serious, right? So if the top expert doesn't really quite understand what's going on, then maybe we have to get back to the drawing board, understand things a little bit from scratch. So I have this code, right? So what we cannot create, I really don't understand, right? So there's many ways since the inception of deep networks, back in 1940s, people have made the architecture, structure, operator has always been sort of inspired by biology, right? Or we draw inspiration or similarity, allergy, or to emulate things we do in the natural neural networks doing. But where did that come from? Why the nature follows those rules? Then you wonder a little bit, ask yourself a little bit very uncomfortable questions, right? So this is, at some point I start to realize that we have to clarify what network we're really trying to do, okay? And what are the very basic, ask the very basic question, right? Why doing it is better or worse, right? What is the measure of goodness, right? So it turns out later on we actually realize this, there's actually trace back to very fundamental questions in pattern recognition or in machine learning, right? Why do we process data, classify data, compression data? Turns out that there's or clustering data, right? Why we process data the way we want it, right? But what do we gain out of it? So this notion of data compression, making things compact, start to stand out, right? So we try to optimize something, right? And once you take that viewpoint, you actually start to realize then, right? What are really deep networks, if we try to learn something from the data and represent them in the very, very canonical way, just like in control theory, right? We have a nonlinear system, we linearize it. Even when we have a linearized system, we canonize it, right? We make it convert to the canonical form, right? So once you realize that we're really just trying to find some canonical representation of data, something interesting happens, right? The deep networks, the structures, architectures, parameters, operators, all just rise as a means to the end, right? They're just natural. That should become necessary conditions to achieve such objective, rather than you come up with a try and error. So this hopefully today, we give this little bit of framework, right? I'm not saying this says everything about deep learning, but actually it's a sort of consistent framework. It's a plausible theory, right? That opens many open problems, mathematical, theoretical, and also algorithmical, and even applications. So, to get things started, right? We try to study this from a very minimal assumption, right? Or with a very clear objective. That's actually what we call the first principles, right? So one thing, the way that we're dealing with high dimensional data, we can classify them, we can separate them, we can cluster them, because they actually have very different structure, very good structures, right? So one minimum assumption is that those data lies on each class, lies on very low dimensional manifolds, right? We'll be more specific later. This can be very flexible, but I'm assuming data first, they are very low dimensional, actually. The intrinsic structure is low dimensional. Second, that the different classes are separable. Those are two minimum assumptions. Now, with that assumption in mind, we start asking what about all the data science, right? What the data analysis we're trying to do, right? I forget about all the names, right? These days, people just baffled with hundreds of different names. People call all the different process completely different names, right? So I have a sort of a joke, right? The mathematics is giving the different things the same name, right? That's Henry Poincaré said that, right? Is the art of giving different things the same name. But I think machine learning has a tendency to give different names the same thing, right? The same thing, different names. So that actually can cause a lot of confusion. So then if you realize, examine what everybody does these days with data, that's really just very, very simple three tasks, mathematically speaking. Why don't we do interpolation, right? Figure out which points are similar to each other. Well, who are my neighbors? So I can do interpolation between them. If we're able to do, those are called clustering, whatever, right? Neighborhood, nearest neighbors, and so on and so forth. And once we're able to do that very, very well, then we get a little bit bold, right? We be able to extrapolate those things on a line or a curve. I'd be able to extrapolate them. That's called classification. When new data points come along, I know which class to assign to. Finally, right, of course, we don't just satisfy with data, explaining with data, which is very expensive, can be very, very heavy in memory. Then we try to find a very compact representations, right? We fit a line, fit a model, right? And then that's actually called a representation learning. So that there is that, right? So honestly, despite all the hundreds of different names people call them, nothing has escaped. At least the current practice of deep learning or artificial intelligence or data science, big data, nothing has escaped from these three categories of problems. Okay. Now, I mean, of course, 10 years ago, deep learning come along, try to say sort of forget about those tasks, so let's lump everything into the whole black box, right? Specify as input of the data, output, let's pick some labels or some function values. I'm just using classification as example, right? Of course, this mapping could be very complicated. I use very deep networks to model it. There's a lot of analysis of what the capability of the networks. But to practitioners, there's some good part about this, right? It is actually simplify, right, the practice. If I have tools to do this, right, the lower the bar, right, I just have to fit the data. Now that's why it's so popular, right? But from an understanding point of view, from a theoretical point of view, this is actually also a bad thing to do, right? Because it's a black box. A lot of things gets lumped together, right? Different components, different pieces gets lumped together, right? So of course, one way people do this is to learn this mapping. Of course, is to have the output of the network matched with the label, class label. One natural measure is just the cross entropy between the labels and the output of the network, right? That's very, very popular and also very, very successful in many of the practical tasks. But when there's a big elephant in the room, right? People tend to talk about it, but not very serious about it, right? So, for example, if we know the network is large enough, since people know this a long time ago, network can represent any input-output relationships. For image classification, I can arbitrarily shuffle the labels, even shuffle the pixels. I can perfectly fit the training data, right? People know that a long time ago, and theoretically and experimentally, right? Then you ask your question: if I fit arbitrary input-output, what do I learn from it, right? It's not very clear statistically, geometrically, what the network is trying to learn. And by the way, I practice deep network, although despite all the empirical success, right, we know serious problems with them, right? There's really no theoretical guarantee or rigorous guarantee of any of the performance, right? People say if I use convolution neural networks, that seems to be invariant. No, actually it's not, right? It's the highly engineered neural networks, right, in industry. If you test them very carefully, actually they're absolutely not invariant. Right, very small deformation can change the output, and also they're not very robust to change your pixel values and so on and so forth. Right, well, we know that. So yet, despite all those empirical success, those are the issues, right? Really interest our theoreticians trying to understand, right? If I be able to successfully feed the data, what do I learn, especially about the data, right? Interpolating, extrapolating, or representing the data. there has been some theory, people actually trying to understand the behavior of deep networks, right? Information bottleneck is one, right? Representing one says that really that the process of deep learning is trying to extract features that are most correlated, the information, right? That correlate with the prediction. And then throw away all the irrelevant informations, right? Hence, you maximize mutual information between the output of the data, the feature you learned, with the label, and minimize the mutual information between the input and the repetition learned. This actually framework actually helps understand, indeed, sort of describe many of the current practice of deep networks, right? In terms of the qualitative behavior of the neural networks. And there's some limitations, of course, immediately if you notice, right? So this assumption heavily relies on the Y output, right? If I change Y, the whole analysis changes, right? Because it's the, and it doesn't necessarily, as I said, I can be even arbitrary. Then what do I learn about the data? We know data science is all about understanding what happens to the structure of X, right? So can we shift the attention? So this is still attention about Y, the output of the network. Can we shift the attention back to the data? Understand why certain labels are plausible, right? So that actually, and actually there's a bigger elephant. I will connect back to the history a little bit, right? There's a big elephant, and very rarely people talk about it. I mean, we realized seriously about 10, 15 years ago, right? Almost all the different networks theory starts with information theoretical formulation, right? Just like an information bottleneck. We try to minimize mutual information, we minimize the Kell divergence, we minimize entropy, we minimize maximum likelihood. Serious problem. What? From computational point of view. Almost all the quantity I mentioned here, right? They're not impossible to evaluate for generic distribution. So if you're not specific, unless for very special distributions such as Gaussian, you have closed form, none of them is even well defined. Well, also when also experientially to compute. Second, we all know, right? When you're dealing with high dimensional data such as the images, the informative structure are highly low dimensional. There are zero measures in the space, in the images. None of those quantities is even well defined, right? The support is zero. So what are you talking about when you're talking about Kell divergence, right? Distance between distributions, assuming they're generic distributions. They do not even exist. That's why in practice, people approximate, right? Oh, let's do a W distance, the Earth moving, right? Because they realize the issue, but they're not treating them very seriously, right? Oh, we can approximate. We can do some variational bounds. We can just approximate those things, right? After a couple of iterations of approximation, you really know the theory and the framework formulation is completely disconnected with practice, right? So how can you expect such a theory to make any prediction to guarantees of the performance of the practice, right? There's a huge serious gap. I call it the computational gap. So we realized this problem when we were dealing with, Kelly mentioned that Renee and Shankar, we worked on the hybrid systems and also work on the image segmentation clustering problem many years ago, 15 years ago. We realized this issue, right? And there's a we cannot, even for problem, we're trying to segment the images, clustering images. Those are high dimensional data with highly degenerate structures, such as subspaces. Even making the simplifying assumption, your structure are just the linear subspaces. You cannot avoid those caveats, right? You have to deal with the low dimensionality of the structure head up. You cannot beat in the bushes, treating the, oh, they're just some generic distributions. I'm going to just write down those formula, pretending they exist. No, they don't. Okay, you cannot compute them. Then why do you write them down, right? So I'll use the clustering classification as example, and we'll see how fundamentally connects to the. We encounter the same problem. This is about 15 years. We're dealing with the clustering problem. Very, very simple, right? The simple problem in pattern recognition, simplest, right? So we have data lies on different clusters. How do we cluster? Well, statistical 101. Well, how about we write down as a mixture of distributions, right? Everybody does that. We teach kids how to do that, right? Write down as the mixture of distributions. Pi is the proportion, pj is for each component, right? And then we do maximum likelihood, right? So how do you do this? This is a linear problem. Let's do EM, right? That's mixture of Gaussian. Everybody does this. You actually by the way, back in the 90s, Hinton was doing this problem, using this to do society. Unfortunately, especially for high dimensional data, this doesn't work. Okay, we were dealing with not even for subspaces. Okay, because this quantity does not even exist. of the support is not even well defined. Then why we're teaching our kids to do something we know it doesn't work, right? So at the time, we actually realized that if the data is the distribution is degenerate, we have to do something else. It's consistent with the same principle, however, has to deal with degeneracy. One basic idea is that then ask yourself a very uncomfortable question. Why do you want to cluster your data? Why cluster your data is a good thing? How do you measure the gain of the clustering, right? So it's a very simple idea, very fundamental, is that, so for example, data is like this. If I'm able to, so if I save all the data, I need a very big bag to solve them, to save them, right? Well, if I'm able to partition them in a very judicious way, then I only need a very small bag for each pieces. Right? Hence, it's a very simple idea, right? If the whole is greater than some of the parts, then I just break it into parts, right? Then all I need to is some measure what have gained from it, right? So therefore, you need to measure. Of course, here the bits is just to choose the units, right? You can use the dimension, volume, whatever units you choose. We're computer scientists, so we use engineers, we use by bits, right? So the whole question is that really boils down, if you have a bunch of data, what is the number of measure? Do you have a very accurate scale, right? It tells you the volume of your data, right? Turns out a very magical formula comes along, right? Of course, with all the ideas from information theory, right? Rate distortion. If I'm converting continuous data in the high dimensional space to binary bits, I need to do quantization error, right? Subject to a quantization error epsilon. And this is actually formula that give you a upper bound, very tight upper bound. Actually, in the Gaussian case, it's optimal almost, right? That the number of bits, binary bits, you actually need to save the data up to that precision. It's called a rate distortion, at least the approximate version. It turns out that very magically, this formula is exactly the same formula, including all the constants. You can derive from two ways. One is from purely probabilistic way, assuming your data lies on a Gaussian, or the data lies on the pure low-dimensional subspaces. And you can derive this algebraically. You get exactly the same formula. It's very, very magical about it. And we'll see, actually, you can derive the whole deep networks from it just in a second. Just remember, it's log determinant of something, right? Then, at least for clustering, at the time, we found that there's something interesting, right? Then the clustering becomes a compression, right? The reason I cluster my data is because I can gain, right? I measure before and after the partition, which one is using less bits. So it basically become bin counter, right? Nevertheless, the formula measure the bits, but doesn't tell you which way to partition, right? The cluster itself is still a very combinatorial problem. You have to try all possible partitions and then check which one gives you the most compact partition, right? So again, turns out that this measure is very magical. It's very tight. Then we can just use it for some very greedy fashion, right? For example, you merge data. You can start with every point is separated, and you merge them only that you can save bits, right? Them after merging. So basically, the formula give you a comparison before and after, whether you should do it or not. You gain something from it. So this is a very simple clustering algorithm, but it actually works magically. But to optimize this codiness, right? Even data is highly noisy, highly outliers. At the time, is by far the state of art, right? Except a very beautiful base translation behavior, just like a statistical physics, right? To this day, there's tons of open problems. At the time, we didn't even realize how important they are, right? We didn't bother to analyze them. Right now, it still remains open for people who are interested in mathematics. But at the time, it's really what we remember. We derived this method, try to do image classification to deal with degeneracy in this data, right? And it turns out it works magically. Before deep learning, this gave the state of art. See, this is a completely unsupervised, right? Purely objective measure. There's no heuristics, no empirical whatsoever, human intuition whatsoever, just purely compressed images. Give you the state of art segmentation of natural images. Okay, but of course, everybody know what happened shortly after that, right? And then the deep networks come along, everybody start to do supervised segmentation. They start to label the data and they try to emulate what a human does, right? The game's changed. But now there's a shift back to the unsupervised learning. We'll get to that in a second. So now the second thing is that, so if we're able to do compression a little bit better, so what about classification? We get a little bit bolder, right? If we're able to figure out the pieces, then if new data come along, we know how to assign them. It's the same story short, right? It's again, if the cluster are degenerate, maximum likelihood doesn't really work. right? Stop teaching kids to do this, right? This is just not the right way, right? It's good conceptually, but definitely in practice, it's a disaster, right? No wonder people in practice do classification, they train supported vector machines, do neural net. Nobody does this, right? Nobody maximizes the likelihood. Turns out there's a remedy, very good remedy to the likelihood, right? To deal with degeneracy. Again, the same principle. Why do I assign a new data points to a cluster? Maybe only if I incorporate that points into that cluster pays the minimum number of bits to explain it, right? So this is new data points. So we call it the minimal incremental coordinates principle. Again, it's like a bin counter, right? Which cluster pays less number of bits to explain new data, you win, right? And yet this is very naive, right? Almost naive to the bone kind of bin counting business, precisely theoretically doing the right thing. Not only actually when the data size goes to infinity, not only actually is exercising, practicing the maximum likelihood, it actually regularizes for you when the distribution are degenerate with the quantization error, right? So it's precisely that's the map. And also, not only that, it added extra term. It's very magical. We didn't realize after iteration. At the time we just said that when the likelihood is equal between two clusters, you will prefer the cluster with a larger geometric dimension. That's it. I will see. Actually, turns out this formula is very, very magical for deep networks, right? So this is start to be connecting this. But at least at the time, I just gave you a qualitative behavior. What did the classifier looks like, right? So compared to SVM on the right with the kernel, and this is the behavior of nearest neighbor, right? But you can see that although this is a purely non-parametric classifier, but it actually implicitly learns the low dimension structure. It's truly extrapolated, right? It learns the low dimension distribution of the data. There's no sample observed in the training, but it actually gave you a boundary pretending the data, extrapolating all the way to the left. Right? So at the time, we realized this is actually conceptualized the right thing, learn the structure, and utilize the classification. But we were not very, we published a NIPS paper, that's about it, but it's really not very useful. Why? Two reasons. This works for, remember, the rate reduction works for linear subspaces or Gaussian. What if your data is nonlinear? Second, it's non-parametric, right? Then it's expensive using data to explain data, right? So that brings us to today, right? So what if, so we stopped there about 10, 15 years ago. We realized that, yeah, we learned something interesting, but now remember those two issues, right? What if, remember in the clustering classification, we're still staying in the space of X. We never touch it. We never change the data. We do clustering classification based on data themselves, right? What if you are allowed to deform the data? Right, I learn a mapping. If my data like this, I want to convert to a canonical form, like orthogonal subspace, linear subspace. If they're nonlinear, I make them linear. If they're not barely separable, we make them discriminative, right? And also by the end of the day, we get a very compact representation, right? So that also it's become parametric, right? So this is actually my wish list. At least we realizing if you're allowed to do such a mapping, you can resolve those issues. Right, difficulties. Then it comes with a question. Ask yourself again, same question, right? What is a good representation then? What do you want? What do you really want, right? And why a deep network shows up is a good idea. So then just be very, very specific, right? Just like in system theory, we can convert it to controllable or observable form, canonical form, right? Be very specific. Make a wish list. What do you want, right? So if we're allowed to do a mapping from X to Z and then some other spaces, so some continuous smooth map, right? I can ask, so in the context of classification, for data belongs to the same class, we map into a subspace, right? Make them linear, make them low dimensional. Or for data from different classes, we make them incoherent, separate them as much as we can, right? And also for each class, yes, I'll compress the dimension, but I want to keep all the intrinsic diversity of the data, right? I don't want to just fit a one-dimensional label, one hot label. Why? Because, well, apple, orange, right? I want to know all reasons separate apple from orange or other classes. Not only the color, but also the shape, but also the leaves, right? All the things. Don't forget, there are some computers or cell phone called apples too, right? So those are the very simple issue, right? We want our representation to be diverse and distinguishable. I keep all the features differentiated. So turns out, actually, if you use the cross entropy in a very, very straightforward way, actually doesn't have this kind of properties, right? And there's a neural collapse phenomena. It will turn the later part of the network will always map the features into one dimension. We'll see that empirically. Very, very striking. Now, remember this game, right? We are trying to have our data. We try to map it to our feature spaces. And of course, the question is we need to measure how good the measure. Always ask your question, how are you going to measure the goodness of the representation, right? Oh, well, with all the features, right, at least I can measure the zero order statistics or, geometry, right? Volume, how big the feature has spanned in my feature spaces, right? Remember, the rate distortion is precisely give you measure the volume, how many spheres, how many epsilon balls packed into the space of the data, right? We already know that. What if your data has intrinsic structures, right? There's multiple classes. We can partition it. Then this using the entire blue space is a waste, right? So hence, if we're able to classify the data, right, individually, then the actual volume or bits I assign is the sum of all the bits for all the parts, right? So don't be scared by this expression. It's very, very simple. It's exactly the same darn expression, right? Only that the pi just sift out which points belongs to which class. That's it, right? So you partition to k class, k clusters, right? This is just average number of bits. Add them together, rate, average them together. That's it, right? It's the same formula applied to k parts, right? So pi is just the recording the membership. It's a matrix, which point the ith point belongs to j's top. That's it. Very, very simple, just mathematical notation. Right? Then this is the issue, right? If I save all the data with one, I don't distinguish them. I pay the price with the entire blue space. If I separate them apart, I only pay a much less price. Hence, the difference gave me a very good measure how good the representation is, right? It's a very, very simple idea, right? The total coding length versus the parts. So also philosophical wise, right, it's very, very simple to answer, right? It's basically similarity contrasts, the similarity contrast. That's it, right? I want the difference to be as large as possible. And this is in terms of bits. And this formula looks a little bit complicated. It turns out this is very, very magical. We'll have a lot of fun with it. You can derive the whole deep network from it, architecture, parameters, and operators, right? But intuitively, this is simple to the bone. What the reason that this formula is measuring, right? Remember, if I data lies on two subspaces, right, left and right. So if I don't care about the internal structure, then the number of epsilon ball I pack in this whole space is the blue balls, right? And if I able to classify them, cluster them properly, then the number of balls I can quantify encoded by data is those as green balls. Then that delta R, we call the reduction, the reduced, right? The difference is exactly the number of blue balls. That's it. We count in the number of blue balls, right? There's a lot of measures studying the metric entropy and so on, right? Back in 60s, 70s is a hot topic. But once you borrow those ideas, right, realizing the delta R is measuring the space in between, naturally give a measure why we prefer the left. Why? Because left one, the subspace are incoherent, are very discriminated, right? Very regular, very canonical, right? Hence, the blue ball gets maximized. By the way, there's a very, for mathematical-oriented folks, right, there's a family of inequality called the Braskem-Leb inequalities, right? Terence Tao, all the famous mathematicians studied it. When this achieve maximum, right, minimum of those ratios. Those are exactly the ratios of the volumes between sum and the parts, right? We just realized this a couple of weeks ago, and there's actually a whole bunch of works in that direction. So, but at least for engineering point of view, this is similar nice, right? So that if I want to, let's give me a measure to tell me how good my representation is. That's it, right? I can compare different representations now, right? So if I map X to Z and the delta R give me, of course I can try to maximize it, right? The larger this difference, the better. So hence come with this maximum coding rate reduction principle, right? I try to sift out for all representations, the one maximized difference. Of course, you still realize, oh, if I'm trying to maximize the number of blue balls, what if I scale, right, the right-hand side twice, 3 times, 5 times, right? Then the epsilon ball will be more than left, right? So of course, that's not fair. then what do? You normalize. Before you compare, you have to normalize the scale. Hence the normalization per layer, right? Batch norm, layer norm, instance norm, spectral norm. God knows how many other norms, right? But we know whenever we normalize something, we try to compare something. Now we're to be very specific. You're comparing the rate reduction, okay, in terms of bits, right? So in mathematically, all the normalization turns out they're actually absolutely equivalent. We actually, for British norm, map all the data to the sphere, they're all equivalent. So the question is, I try to convince you, right? Maximize delta R is a good thing, but remember our wish list, right? We wanted to get this high level representation. Does minimizing the bean counting business give you those high level concepts? Yes, it does. Turns out just by optimizing those balls, number of balls, turns out that you actually, when you achieve the maximum, the configuration of those subspaces, precisely each class become a subspace. And not only that, they become orthogonal if their feature space is large enough. Not only that, the feature in each class subspace become nearly isotropically distributed. Right? Again, as I said, there's a counter work on a Braskamp lib inequalities. Turns out in the other way around, if you minimize the ratio, you end up with Gaussian distribution. Very, very interesting mathematics, but this is a sort of early results, right? But this shows under broad conditions, optimizing this rate reduction indeed gave you the desired configurations. Therefore, we remedied the Aristotle's thing a little bit, right? For representation learning, not only we want the sum, the whole is larger than the sum of the parts, we wanted the sum is maximally larger than the sum of the parts. So hence there has been, people try to also encourage incoherence in different classes. For the interest of time, I'll skip some of the details. I can share the slides with you. And also, this actually has flavor of contrastive learning, contractive learning, right? If you've heard those terms, right? Turns out this simple objective has all of them in there. Not only in the contrastive learning, just doing pairwise samples. Here, you measure volume for arbitrary number of sets, right? Individual samples or sets of samples, it's all in this measure, one measure. And for the first time, right now you can have the game, and then you actually can train deep networks with this objective, right? Everything else is equal, but right now it's very simple, very different now. I don't have to, after train my network, to look at the accuracy on the test data. While I'm training the neural network, I'm monitoring 3 very physically or statistically meaningful quantities now. I can monitor if the whole set is expanding, each part is compression, and the difference is getting enlarged. Right? You can actually monitor the process as you train the training data. You don't care about testing because it's all about learning structure for the data given to you. And you can start to see after you converge, right? It's actually something very striking. This is on CIFAR 10, very practical data, very noisy random data, right? But the feature learned across 10 classes, it's absolutely orthogonal, right? And not only that, everything, by the way, this is a comparison between the cross entropy and MCR. Right? Everything is exactly the same data, same networks. The only difference is object function, okay? So you get the orthogonal subspaces, and also not only that, each subspace is evenly distributed. Not like cross entropy, start to shrink to one dimension, the fit one hot labels. And even after all the features, right, keep in mind, there is a lot of crosstalks between different classes, right? Here you get purely orthogonal subspaces. There's no crosstalk, very rarely, once you converge, of course. And also that remember, not only do I get a one hot label now, I get a 10-dimensional, each class, I get a nearly 10-dimensional embedding, right? Just compute each of those coordinates, find out images, align with each coordinates, principal components. Actually, you can see that the automatic sort out your data for you after the embedding. So you mapped all the birds to 10-dimensional subspaces, and each direction actually is very, very semantically meaningful. You get never given those in the labels, right? Also, that since we are no longer fitting each individual labels, try to have the network explain every individual labels. We try to collectively learn a model for each class, right? Suddenly realize the model is very resilient to class label corruptions, 10%, 20%, all the way to 50%, right? You learn subspace collectively. Because I only have to compress data collectively, right? Since I cannot compress, I forget about them. Right? I try to fit a single subspace to, or some manifolds to the data, right? Suddenly you realize it's much, much more robust than you try to explain every single potentially noisy label in your data set. Also, you can apply to the, if you don't have the label, you can do unsupervised learning. The expansion tends to be works very, very well. This is the details in our paper. You can take a look. Also, the simple objective measure actually give you the state of art self-supervised learning results. And this is not even the best we can do. Now, the last few times I try to convince you. So are we happy, right? So at sometimes, so I told you, right? I started this trying to understand what deep network is trying to optimize. Are we happy, satisfied with this? Yes, a little bit, right? In a way that we realize that at least the object function becomes somewhat just unlike a cross entropy, just fit the label. At least the object function try to characterize some intrinsic structure of the data, right? Learn embedding of the data, linearize it. And that's one thing. A second, we realize that indeed the subspace, the feature we learned is very geometrically statistically meaningful. There are also close subspaces, right? Third, we realize, oh yeah, indeed, by doing this, we end up with a network that is much more robust in terms of label noise. Okay, not necessarily input, but actually the output, right? So that in that sense, we're a little bit happy, but there's a big but, right? So the question is, how do you model the F? We still borrow, right? We still use the ReduNet, or we still use whatever your favorite, right? VGG and anything. That's still a black box, right? Then how wide, how deep? It's still not explained, right? What are the linear operators, right? Why deep network is the necessary, right? And so on and so forth. Especially all those linear nonlinear operators. So why do we have to interleave them that way, right? What is any other choices? By the way, we've all used the convolution neural network, right? I think it's magical, right? I'm a computer vision person. I use the convolution all the time, right? But everybody realized, right, from the very beginning, the convolution we deal with in convolution neural network are very different from what we do in image processing, right? Image processing, the convolution are separable, right? A 2D convolution kernels, right? Patches. We learn from patches, from wavelets, from Fourier transform, right? But the convolution in deep networks are all 3D, multi-channel convolution. Why? Has anyone explained why that is the case? Right? No, we just use it. And if you don't use it, the performance is worse. Why? Right? So these are all the things. The question is, can we actually open the box, make things make sense? Why? So one good thing is about very clear about the objective, right? Is that honestly, that's your starting point. You don't have to, take deep networks for granted, right? So this is the object we try to optimize. Then can we just go directly to optimize it, right? So this is actually the object function. Remember, this is the first part is the total, expansion term, right? We wanted for the whole feature space, and the second one is the parts, right? So we have to maximize the difference between them. And I just this looks like a very non-linear, non-convex problems, right? But one thing we learned from deep network is that how do we optimize it? We can at least try with the greedy descent, right? Remember, also we have to normalize the feature. Hence, we're doing projected greedy descent, right? Computing the gradient as a step, and then project it back to take the step and project back to the constraint set. Normalize features. As soon as you do that, something magical happens, guys. What happens is that those gradients start to see very, very clear structure, right? They're not at random, right? The first term is actually some matrix hitting your data. The second term is also another linear operator hitting your different class of the data, right? The first term is actually trying to expand the feature space. All the second terms are trying to compress individual classes, right? Those are piecewise linear operator acting on your data, doing this way. By the way, those operators, whoever are familiar with statistics, right, you should feel very excited, right? You know what it exactly is. This operator acting on your data is precisely computing the residual, remember the word, residual of the autoregression using all the data points to explain your point of interest, right? Do a ridge regression, and the EZ is exactly the residual of that. How good other data points explain this particular point, right? Hence, it's residual. E and C are computing the residual for you. If you try to expand, you make the residual larger. If you try to compress, you make the residual smaller. That's what really each gradient component is doing. Schematically, this is very, very simple, right? So remember our goal, right? We have those functional points. We try to, they are like non-dimensional submanifolds. We really try to push them to the orthogonal subspaces. That's all. But we don't know how to do it. But at least locally, I can compute the gradient, right? I can follow the gradient flow to make the things a little bit better, right? Incrementally, right? So it turns out that those incremental operators are precisely the linear operators, right? Expansion and compression. Now, there's a little bit of issue here. In order to compute those piecewise linear mapping, right, you need the membership, especially for a C part. You need the membership, though this point which class it belongs to. But don't forget, right, the CZ is precisely the residual. You already have it, right? And you can approximate the pi, the membership, using a soft classifier, because based on the residual, you know which class it is closer to. By the way, we're doing gradient descent. Everybody knows gradient descent, right? You don't have to be accurate. As long as you're in the right direction, you're fine, right? So basically, there's gazillion. Then you start realizing, there's gazillions way I can approximate this classifier, right? I can use a soft mask. Well, if I restrict all my features to the first quadrant, then I can use the red rule, right? The different choice of the linear activity is just you know what you are approximating. Then you're fine. They actually all works if you do the engineering right. There's nothing special about any of those. Now, once we have the gradient descent, let's just write down the algorithm, right? We can compute the gradient now, take a step, Z, and add to the previous iterate, right? That's exactly standard gradient descent algorithms. Since we're all engineers, we like to draw diagrams, right? Let's just draw diagrams. From the previous iteration, we pass through those linear operators. So we add identity. Remember, there's the Z, and we pass it through sorting, gating, grouping, and add them together, normalize them to the next iteration. What does this look like to you? Right? This is exactly a residual network. Not only that, right? We know exactly what the residual are computing. Actually, not only that, later on people found out, right? If I add parallel groups to the channels, the performance is better. It's called a res next, right? The meta structure is exactly the same, right? They're basically emulating the gradient descent. The gradient descent is exactly what we call the ReduNet, right? Computing reduction, right? Hence the reduction network. But there's something you realize, there's something very strange, right? For all the network, you need to randomly initialize them and do backpropagation to learn those parameters, right? Here we don't. Everything is computed in the forward fashion from starting the first layer, right? We even gave you the closed form formula for what those E and C's are from the previous layer, right? There's no backpropagation is needed. All the linear, nonlinear operators computed, forward constructed. Right? Maybe you heard, right? People are training gazillions, 1.7 billion parameters, right? Google's mixture of experts, rich transformers, right? Has GPU much bigger than GPT-3, so on. Look at their meta structure. They're exactly the same, right? There are 4,000 branches of they called experts, right? And now we can even tell you what the experts are. They're precisely classifiers for each class. They'll try to group your data, right? Compress them, find a good representation for them, right? By the way, their switch operator is exactly the softmax. They found it empirically, right? Here you derive everything. You know it's doing classification. That's it. So does this work? Yes, it starts to, right? I mean, simulation can have a lot of fun with this, right? So really that you throw 1D, 2D Gaussian, really that this process, you can build very deep networks, right? Actually, in the 2000 is definitely not necessary. The students just want to have fun, right? And basically, it's it's optimization. You can let it run forever, right? You don't never have to worry about the networks is unstable or whatever, right? And it's all forward computed, right? Once you construct it, you're done. Right. It really does what you want. You get squeeze every group to a low dimensional subspace and make them orthogonal. That's it. And also for, of course, we're not just dealing with clustering data, right? In the vector form. Very often we actually also doing the care about there's additional structure in the data, right? For example, for image classification, the rotated or translated version also need to belong to the same group. There's been a lot of work trying to understand, convolution networks or using equivariant networks try to do this, right? But there's a couple of recent paper you should read, right? Despite all this engineering, all this networks actually not, there's no guarantee for that. right? Very small translations or deformation can make the network go crazy at some point. In our setting, this is actually very simple, right? So at least in terms of statement, right? All you have to do is to map all the translated or transformed version into the same subspace. That's it. Mathematically, it's very clean to state, right? The question is, can you do it? Let me close my glass. Yeah, so there's some sounds in my eyes. So this is just the mathematics has become very clean. The question is, how do you do it, right? Let's use one-dimensional signals to illustrate this, right? So you have a one-dimensional signal, then all the translated version needs to belong to the same group, basically, same class, same subspace. I try to map to the same subspace, right? I collected them into the matrix, right? Each column representing a different shift. You get a cyclic matrix. Then all your job is to let's compress all of them together, right? Because you want to map all of them to the same subspace. As soon as you do that, you realize something very interesting. Remember all this gradient linear operator, they automatically become a convolution, right? You don't get to choose them. The task of compression data of this form stipulates you have to use convolution. Not only that, it tells you what the value, which convolution you should use, right? At least incrementally, right? So you don't get to choose a form, you don't get to choose a value, right? EEC channel are computed for you from the data. And also there's actually an issue, right? If you try to map data of this form, a signal with a cyclic form usually span the entire space. They're not subspace anymore. So you cannot separate them, right? Hence, there's a fundamental trade-off. Turns out you cannot allow arbitrary shifting of your signal and also allow arbitrary superposition and claim they should belong to the same group. No, you cannot do that, right? So because you cannot separate fish from ducks. The only reason under condition you can't separate them is you have to assume the classes of data are sparsely generated. You can only allow sparse superposition to allow to linear separability. So therefore, you need to really to lift this image, assume that it's a sparse generator in some feature spaces, right? So how do you compute those sparse code, right? There's a whole industry about compressive sensing, teach you how to do that, right? So one very simple way is just to hit the data with multiple kernels, right? Lift it, then they call analysis field kernels, right? Keep in mind here, we are not care about the representing the signals in a very precise way, right? Unlike compressive sensing. Here, we only care about give me some sparse code, at least they are separable from other classes, right? So much relaxed requirement. Hence, you actually just hit your data with multiple channels and make sure they are sparse, right? And even random features would work in general, as long as your data has low dimensional structures. Now, but once you do this, suddenly you convert a single channel signal to multi-channel signals. How to compress them, right? You are compressing this humongous space, right? Multi-channel and sparse signals. As soon as you do that, you just pretend, right? We're just compressing, just do the gradient descent, write down the rate reduction, right? Do the compression. Something magical happens. As long as you start compress those multi-channel sparse channels, those operator, E channel, C channels, operators precisely becomes multi-channel convolution, right? This form pops up, right? You don't get to choose it. You have to use multi-channel convolution. All the channels talk to each other, right? So suddenly you can realize, right? This is very interesting. You start to get the derived architecture multi-channel convolution network purely from the data themselves, right? Not only the form, but also the value in a forward fashion. Compared to, there's actually people try to construct the deep networks from, explicit using wavelets, right? And the modular wavelets to do scattered network, even can assume, ensure invariance for general signals. But here, the difference is that we don't care about arbitrary signals. We care about the data you're given to me. I find the best representation for you. Hence, the number of channels used is always fixed, right? Here, once you just do wavelets, right? Each layer, you have to use all the bases. The number of bases just explodes, right? That's why you cannot build very deep networks. And also one thing is realizing, computing this operator is not a picnic, right? The C is the number of channels, N is the dimension of your signal. In the case of image, that's the number of pixels, right? This is the humongous inverse to compute. Turns out that, again, this is not arbitrary matrix. This matrix are blockwise circular, right? We all know in the frequency domain, right, all circulant matrix become diagonal. Therefore, right, if you compute the inverse, construct those operators in the frequency domain, the complexity reduced from n cubic to linear in n. This is I'm very surprised to see this, right? This is evidence that to construct neural networks, there's a tremendous advantage to do it in the frequency domain. That's why actually our visual cortex is doing this, right? You probably know neurons actually precisely computing in rates, not in magnitude, right? The frequency they fire. Probably nature already learned that it's much more economic to build neural networks in the frequency domain. And here is a reason for that. And for the first time, you actually can write down the entire neural networks, right? In a purely white box in the frequency domain, right? So you can actually do that. Every single parameter, every single nonlinear operators into the form, everything explained for, blamed for, called for, right? You don't get to choose them, right? As long as you set yourself the following task, you have data, high dimensional data, you try to map them, multi-class data, you try to map them into a canonical representation, linear incoherent representation. Then everything becomes necessary. You don't get to choose them, right? So sparse coding is for separability. You cannot, you cannot assume arbitrary invariance and also superposition. No, you cannot. Right? Mathematically, that's impossible to separate. Right? Or deep networks that try to maximize reduction to make this configuration better, step by step. Right? All the spectral computing is to save your money, save your cost. Right? And it's much more economic to do. And the convolution, multi-channel convolution, normalization, nonlinearity, all just become necessary components. Right? You don't even, there's freedom to choose them, but you know exactly what they're doing. They're supposed to do. And does this start to work? Yes, I guess some very simple cases, right? So that you can, for the first time, we are able to build neural networks that truly invariant. We're not just invariant on some tested augmented data. No, we test on every single angle after learning. Okay, there should be no crosstalk between two classes, or you can see that the feature learned between the all shifted rotated version of 1 and 0s. There's no crosstalk. They're purely on orthogonal subspaces. And also 10 classes, the same, all digits. All the translation, again, we're not just augmenting 10 different augmentations. Here is on every single translated pixels. Right? You have the networks to get tested and to check the features if all the classes are orthogonal to each other. And by the way, remember the metastructure of the network we derived has exactly the same metastructure as any other networks. In fact, all the other network looks like it, right? So of course, you don't have to, the number of iterations you can choose, the number of channels you can choose, right? They may not be optimal, right? They may not be adequate, right? Remember optimization, just like I stopped short early, right? So they may not be best. However, they give you the structure, right? If you have additional training data, you can fine tune the network using backpropagation. Nobody's stopping you from doing it, right? First, of course you can, but there's two differences. First, you don't get to choose a network. Second, you can initialize. You don't have to start from random initialization, right? The Fourier construction already gave you a very good warm start, already gave you a decent network, right? You only have to fine tune it. Hence, the Fourier construction is doing optimization. The backpropagation is doing variational optimization. You tune against the past. That's it. Mathematically, it's very, very clean what you're doing. And so hopefully today I gave you a rundown, right? So you can see there's a very, very unifying way to look at what we're doing with data, right? It doesn't matter we do clustering, unsupervised, or we do supervised classification, right? The goal is all try to compress the data, have a more compact representation of the data. Now, if we wanted to use the same principle to learn a good representation, right? That's just a read reduction. We maximize the difference between the whole and the parts, right? And if you just choose, of course, there's a way you can optimize this. If you choose just a greedy descent, the greedy incremental fashion to do, you'll actually get neural networks, right? All the modern characteristics of these networks arise just like from first principle, right? And a very interesting thing is that in the first two tasks, right, we fix X, we try to learn pi, right? The membership. Here for representation learning, we fix pi, we try to learn the representation Z, we allow you to deform X, right? So this is just doing a quick comparison to the classical literature of deep network since the 1940s, right? So you can see that the conventional network is always doing the left, right? So we try to fit input-output relationships. The architecture is inspired by biology, right? There's definitely a design is empirical using different nonlinear linear operators. We try to achieve invariance using convolution plus some augmentation, right? We train them with random initialization. Even after with backpropagation, after we train, we still get a back box, right? We are not very clear what's going on inside there, really, right? Now with compression, everything is completely the opposite, right? The objective is clear, and the layers are just iteration optimization. And by the way, you realize in the network, each layer is doing optimization. There's gazillions of ideas, right, from optimization, 200, 300 years of optimization. We're not saying the gradient descent we use here is just a very naive step, right? You can design all kinds of fancy optimization, much more accelerated, much more advanced ideas can go to give you design much better architectures. And network is entirely forward computed. And the network also, you can optimize it. Once you realize that, you can optimize or fine tune either forward or backward way, right? There's nothing special about backpropagation. And it's entirely white box. Every operator, every parameter, you know exactly what you're trying to do, right? And then after you learn, the final representation is also highly geometrically and statistically meaningful. You learn a canonical form of your data. That's it. Right, so this is actually opens up many theoretical problems, right? I remember also even we realize even the clustering setting, the phase transition, the robustness of MCR, none of them has rigorous mathematical calculation yet, but those are compelling phenomena, right? And under what condition you can achieve the optimality, and also there's now we know there's a qualitative, we know there's a trade-off between sparsity and invariance, but there's absolutely no quantitative study. I just finished the 1,700-page book on this on sparsity, but I realized nobody has studied, right, how to classify class code as a class. There's none. I'm not aware of any study on that regard, right? And also we realize right here, remember, clustering classification is about fixing X, the data, doing the membership, right? Also representation is fixing the classification, learn the deform your data. What if you don't know either one of them? Yes, you can do joint optimization, right? Actually, this works, and there's some ongoing works that many folks are making progresses. And also, as I mentioned earlier, right? Once you realize each iteration is just optimization, gazillions of ideas for optimization to construct better network, more efficient, right? Like and other additional structures. Those remember E and C channel, they're highly, we didn't study, those are a lot of structures in them, right? How to make them more efficient. And we give example of rotation translation. What about other groups, right? Deformable groups and so on. So what other structures? We know, you see, convolution just pop up from compression, right? What other operator will pop up from compression and other groups? We don't know, right? And by the way, everybody talk about transformers these days, right? You're staring at it, right? I mean, people talk about CNN is better than MLP. Transformer is better than CNN. Now people find out MLP is better than transformer. Everybody is doing the same thing, okay? Just try to optimize the configuration, okay? Then if you look at this objective function, to compute the log determinant, you don't need the covariance matrix. You only need the inner product between the data. That's in the formula. Okay, now, since it's inner product, of course, I don't have to inherit the Euclidean inner product. I can learn another basis, right? Transform your data to another linear transformation and compute the similarity in a different basis. We call it a kernel. That's exactly what the transformer is doing. Okay, there's nothing mystery about it. And this is just try to minimize the same quantity. Just apply a global linear transformation to minimize the rate reduction. And there's something interesting. I mean, since we released some of our paper, I get a lot of papers from emails from neural scientists. They actually tell me, oh, we actually realize there's we already know this, right? So for example, that the sparse coding, I know that too. I worked on that. Turns out, I was very surprised that they said that, well, actually, in visual cortex, actually people computing the neurons computing spikes. That's why I call it the spiking neuron. Precisely, everything gets implemented on the spectral domain, not in the magnitude domain. And also, there's actually turns out the recent study shows that the primates remember identity, precisely encode in high-level infernal temporal cortex. Those identity gets encoded in the subspace. There's a 200 neurons. They actually act like a basis. Every superposition representing a clear image of the faces. They're not prototypes. They're not pure memory. They're actually encoding of those faces. That's very, very interesting, right? So sort of the nature, you can see from very simple mathematical principle, you linear subspaces are only structures, and there could be dynamic structure, graphical structure in the data. But I believe the principle of compression should always play a role when you learn graphical deep networks and so on and so forth. You should be clear about what the object is trying to do. And also the other thing is that here, the entire talk, I talk about one side of the story, right? Going from X to Z. How good Z really is, should be able to test it on how Z representing X. Then you should be able to go back, right? And that's precisely the decoding story, right? Again, there will be some very exciting recent developments. So we'll probably report the next time, right? So this seems to be, we are very much on the right track to once you learn a very good representation, in terms of generative power, they are much, much better. So those are some recent work. Again, as I said, this actually somehow our recent investigation connects back to what we did about 15 years ago on data clustering classification from compression point of view. And the most starting paper is probably the ReduNet paper we just released about a couple months ago. You can actually start from there. You get all the references from there. There's also a recent new books give a more broader context on the connection between low-dimensional structures and the deep networks. All right. There's also a website. By the way, don't compare our network with the 10 years of practice, right? Google, Facebook, Microsoft has done, right? All the gazillions big networks. However, right, all the codes they have there, now you know the principles, how to construct networks now, right? We have a humble beginning, but it's purely white box, right? You can already see they start to have a very good promise to showing the ability. You actually can play with them. We released some of those online. If you forget of everything I said today, right, just remember this one line, right? The deep convolution neural networks are actually doing iterative optimization scheme for compression, right? I'm talking about the network structure layer by layer, not the training of the network, okay? The forward construction of the networks are precisely doing the optimization, and we know what they're optimizing now, right? Then fine-tuning is just a matter of variational fine-tuning. Right, backpropagation, forward propagation, there's nothing special about them, right? Maybe just difference is only which one is more effective, which one is more efficient to do, right? But the architecture is doing optimization. So that's all. Sorry, yeah, maybe that's going to be running a little bit over time, but hopefully this give you a more complete story. Thanks.